You're hanging with Hussick, and this video is going to define what an acid is and what a base is. Okay, so in this video, I'm going to try and answer these first couple of questions, and the third one will be a bit of an elongated discussion with some specifics. So the questions are, what are acids and bases? And what are the features and properties of each one of those? And then we're going to discuss the three major chemical theories that explain their functions. And those three theories are Arrhenius Theory. I probably should have practiced spelling that before I went for it, but I think that's right. Arrhenius Theory. And the Bronsted-Lowry Theory. And finally, Lewis Theory. And it's mainly we're going to spend time on the first two, Arrhenius and Bronsted-Lowry. Lewis Theory we're going to toss in, but it's not always relevant unless you're taking IB or AP chemistry, but most high school chemistry classes you might touch on Lewis Theory like I'm going to in this video, but elaborate on it later for certain practical purposes if need be. Okay, so maybe the most practical place to begin is just a comparison of acids and bases in everyday life. So where we come across chemicals that we would call acids or chemicals we would call bases in everyday life. And one is in foods. So for foods, if you're consuming a food that's acidic, it tastes sour. Okay, so one hallmark of an acidic food is it tastes sour. This is something like a lemon or other citrus fruit like that, vinegar, stuff like that, okay? Very sour tasting, and that's because they contain acids. Bases, on the other hand, taste bitter. Foods that contain a lot of bases, I don't know if you've ever had like rocket, that kind of lettuce, that's very bitter. It has a lot of a base in it. Bases are also slippery. They feel slippery on the skin. So it's stuff like soaps. Soaps are made with bases. Acids, I don't know if they have a particular feel on the skin, so maybe there's not a direct comparable there. The reason I wrote acid in red and I wrote base in blue is that there's a certain chemical called litmus, and in litmus, it's just, you may have heard of the litmus test. Litmus turns red when it is in contact with an acid, and it turns blue when it's in contact with a base. So we tend to, if we have the opportunity of using colors, we tend to choose red for an acid and blue for a base for that particular reason. Bases are referred to as alkaline or alkaline. You may have seen this written on the side of a battery or something like that. It's because the salt in a battery or the brine in there is an alkaline base where, if something is acidic, we call it acidic. So alkaline and basic are two terms that can be kind of interchanged. What else? You've likely heard of the pH scale. So the pH scale is a measure of whether a solution is acidic or basic. And for acids, they have a pH that is generally less than 7, although we'll see in later more finer detailed senior chemistry that this isn't always true, but it's generally true. And bases have a pH that is greater than 7. Okay, what if it's exactly 7? Well, it's neither acid nor base, or you might say it is both acid and base, like pure water. We'll get into a little bit more of the chemistry. So acids react with, they react with metals. Okay, and an acid reacts with a metal to form a salt. Okay, or an ionic compound of some sort. Bases do not react with metals. Probably the most common reaction that you need to know about when it comes to acids and bases is the fact that when you mix an acid and a base together, they neutralize one another. Okay, So when mixing acid and base together, they neutralize. So what exactly does this mean? What is neutralization? Well, I'll give you some more details on that. Sorry, before I do that, though, I just realized I don't want to lie to you or use imprecise language. This shouldn't really be, I shouldn't really call the product of metals, of acids reacting with metals, a salt. It forms an ionic compound. So it forms an ionic product. And the other product it forms is hydrogen gas. So it forms an ionic product and hydrogen gas, which is H2. The other thing is it's not every metal, not every single metal is able to react with acid, but some of them. Okay, more on neutralization. Okay, so in an acid-base neutralization, basically it's a reaction of an acid and a base to create a salt and water. This is the most common type of acid-base neutralization. What we also see is that the energy term is here, or produces heat, or it releases heat. This is also known as an exothermic reaction then. What we'll come to find out is really interesting about acid-base neutralization is that the product is not always neutral. So it seems a bit oxymoronic, but the term is being used in a couple of different ways. And as I was writing that last bit, I realized a couple other practical things you should probably know as an introduction to acid and base. Acids are compounds that usually contain an H. Okay, so they usually have a hydrogen in there somehow or another. For example, in HCl, hydrochloric acid, you see a hydrogen there. In ethanoic acid, CH3COOH, you see a hydrogen there. And this becomes really significant in what's called Arrhenius theory, which we'll discuss subsequently here. So this acid, ethanoic acid, this is found in vinegar, okay, just to give you an everyday, a place you might see it in everyday life. Bases, on the other hand, tend to contain hydroxide, OH, okay, so something like NaOH or MgOH2, this is sodium hydroxide. This is found in soap. It's not itself soap, it's in soap, and this can be called milk of magnesia, MgOH2. It's often found in like antacid tablets, you know, like Rolaids or Tums, that kind of stuff. Stuff you don't know much about when you're young, but when you you become an old man with an upset stomach like me, you find out a lot more about that. Okay, so the next bit of this video will be about acid-base theories. So essentially looking at the chemistry of how are these two categories of chemical compounds different? Why are they so significant? Well, the story basically is here that throughout history, alchemists and then later proper chemists noticed that there was a fundamental difference between, we could broadly categorize a lot of chemicals in chemistry into two categories, and we call them acid and base. So what is it about the nature of the actual chemical molecule that qualifies it as an acid or qualifies it as a base? And throughout history, there have been different theories about what the chemical nature of this dichotomy is. And so what's survived is basically the best three theories that describe this for different practical reasons, okay? And those theories are Arrhenius Theory, Bronsted-Lowry Theory, and Lewis Theory. And we're going to discuss those three. Why all three? Well, because two of the theories, well, each theory has its own specific sort of practicality and helpfulness in identifying and using acids and bases. Okay, so where we usually start is with Arrhenius Theory. It's the simplest. It falls apart for some examples, but it works very well broadly to help as an inroad to understand acids and bases. And what Arrhenius Theory basically says is that acids produce H plus when they're in solution, and bases produce hydroxide, OH minus ion, when they're in solution. H plus can also be known as, it will often just be called a proton, right? Because if you think about it, a hydrogen atom with its electron removed is just a proton. So acids produce like basically a free proton, in solution, and bases produce a hydroxide. So, for example, if you imagine HCl, like we said earlier, hydrochloric acid, which is an acid, in solution, essentially, we can consider that, and I probably should have put a little aqueous symbol over here too, because it's in solution. We can consider it as producing H plus and then also producing chloride, but we're much less interested in the chloride. We're really interested in the H plus that it produces in solution. And then if you look at a base, for example, NaOH, like we mentioned before, when it's in solution, it produces the hydroxide ion, and that is of utmost importance, especially relative to the sodium ion. We don't much care about the sodium ion there. Na plus, we care mostly about the hydroxide. Okay, so what's the limitations of this theory? Well, you may notice we're talking about in solution. So it's limited to aqueous solutions. Like this, then you might ask the question, well, can acids and bases only exist in aqueous solutions? No, they can exist outside of aqueous solutions. So that's where Arrhenius theory falls apart. And we'll discuss then why Bronsted-Lowry theory essentially takes over as a kind of better and more ubiquitous, more universal theory of acid and base. But Arrhenius theory is very useful. Okay, the second acid-base theory is called Bronsted-Lowry theory. This is a really useful, really practical, probably the best theory for describing how an acid and base are different for high school chemistry, to be quite honest. So what it discusses is, it says an acid is a proton donor. Okay, and remember, we're talking about H plus being the proton, and a base is a proton acceptor. Okay, what it also will inevitably then postulate is that these always come in pairs. Okay, so the process happens in pairs, and I'll show you that with a couple examples. So, for example, if we take an acid that we looked at earlier, for like, okay, let's take ethanoic acid, CH3COOH. When we put it in water, okay, what we see happen is it takes this proton, which is called the carboxyl proton, because that's the carboxylic acid group, makes it an acid, and it donates that proton to water. Okay, so what the product is H3O plus, because it donated that proton, and CH3COO minus, the ethanoate ion. Okay, so we can see in this process what has happened is the ethanoic acid molecule has donated a proton to water. Okay, if we look at a base example, and let's take a base that we haven't seen yet. This is a base, NH3. So it's a non-hydroxide base. So right away you can see it's not so obvious how this fits the Arrhenius definition of a base. Because how does it generate hydroxide in solution? Well, I'll show you. So to be in solution, just like the last one, basically means we're going to mix it with water, right? So let's mix it with water. And equilibrium symbol, I'll explain later why these systems are in equilibrium. But what we'll see is that this one accepts one of the protons from water and becomes NH4 plus. So this just happens naturally when it's mixed with water. And the result is it does produce hydroxide. Okay, but what you can see is it is very importantly accepting that proton from water, and that's what makes it a base. Okay, so just in case you're looking at this later, it's really critical that you see this is the acid, this compound, and down here this is the base, this compound. Okay, and we can go further into this, but what I was mentioning is that they always need to occur in pairs. Is that, in other words, for every acid there must always be a base. So in this case, what comment might you make about water? If you pause the video for a second and ask yourself, what is water doing in each one of these examples for the acid and the base. And what does that say about water? Hopefully you paused and then you realize that water itself then is able to act as an acid or base. Okay, so this is a very important fact about water. So it's able to act as acid or base. And you can see in the first example, when it's mixed with an acid, it acts like a base, doesn't it? Because it is accepting the proton, which is the definition of being a base. And then you can see in the second example, it is acting as an acid, isn't it? Because it is donating the proton, which we said, according to Bronsted-Lowry, is the definition of an acid. So it can act as an acid or base. And this is a feature, there are several compounds like this, and it is a feature of being called amphiprotic or amphoteric. I think it means the same thing, but amphiprotic is how you often see this. And so water is a really important amphiprotic substance. More on this to come. Okay, so in a Bronsted-Lowry acid-base system, so in other words, we're going to put our Bronsted-Lowry acid-base definition hat on, and we're going to say every time we see an acid acting as an acid, this is the reality. For every acid, there's a conjugate base. There's what we call a conjugate base, which is kind of like the base equivalent of that acid, okay? And then for every base that we see acting as a Bronsted-Lowry base, it's going to have a conjugate acid, okay? And so in general, we could use this format down below that you see here. So if we have an acid, and we're going to call any acid HA, because remember, like, an acid has an H there, which can be donated. We're going to see that that acid, once it donates that proton, and it donates it to water over here, doesn't it? Right? It donates it to water. What's left is this species A minus, and that's called the conjugate base. Okay? So the conjugate base is the deprotonated form of the acid. Okay, so it's deprotonated. So it used to have a proton, and now it doesn't. Okay, so it's the deprotonated version of the acid. Then what's functioning as the base here, as we discussed on the last slide, is actually water. Well, look at this. The conjugate acid for water functioning as a base is this species H3O+, which is called the hydronium ion. Basically, it is another way of looking at H+. Okay, and I'll give you a little blurb on that in a minute. But the point is this. For every acid, there's a conjugate base, okay? So there's those two. And for every base, there's a conjugate acid. And together, where I've drawn the arrows here, we call this a conjugate acid-base pair. So that's a conjugate acid-base pair. I'll show you some real examples after this, and then I'll get you to try a few. And this is a conjugate acid-base pair too, just water and H3O+. That's a conjugate acid-base pair. Might get a little bit sloppy, but you know, the idea gets through. Okay, so here are 3 examples of Bronsted-Lowry acid-base systems. And in each one of these, example 1, 2, and 3, there's an acid and its conjugate base. There's a base and its conjugate acid. So I'd like you to pause the video, see if you can identify in each one of these the conjugate acid-base pairs. All right, so here we go. In the first one, we can see that this is an acid. How do we know it's an acid? Well, we know it's an acid because there's a hydrogen in the compound there, firstly. Secondly, we can see it meeting the definition of a Bronsted-Lowry acid because it's donating that H+ to water, okay? Then over here on the right-hand side, we can see the deprotonated version of itself. That's the conjugate base, okay? So here's your first conjugate acid-base pair. This acid is actually called chloric acid, I think. So acid and its conjugate base. And then you see that water is acting as a base, isn't it? It's actually accepting the proton from chloric acid there. And so the H3O plus is the conjugate acid. The hydronium ion here is the conjugate acid for H2O. So there's the other acid-base pair. Okay. In the second one, we have ammonia, NH3. That's a base. Now that's a sneaky base, but all the NH3, it turns out, this is something familiarity with chemistry. Anything that has like an amine in it, NH3, always turns out to be a base. And how we can tell from this example that it's a base, mainly, is that you can see it's accepting the proton from water because it creates this species over here, right? So that's its conjugate acid. Its conjugate acid is called the ammonium ion, NH4+. And so that forms a conjugate acid-base pair right there. Then we have water, in this case, working as an acid. And, of course, its conjugate base is going to be the hydroxide ion, OH-. So there we go. They have another conjugate acid-base pair. And again, please notice that the acid and the base, the base and the conjugate acid, or the acid and its conjugate base, anywhere we've drawn the pairs, those are always the protonated and deprotonated forms of themselves. The only difference between an acid and its conjugate base is an H+, right? But it's the H and the plus. That's very important because that's how you get the formula for a compound like ClO4 minus, correct? Okay, it's not just ClO4, it's ClO4 minus. Okay, let's go with the last one. The last one, we see an acid here. This is actually formic acid, properly known as methanoic acid. It has a hydrogen there that is actually donated to water. How can you tell? Well, look at what it produces over on the right-hand side. It produces H3O+. So obviously the water accepted a proton, making water the base. Okay, so water is the base. But it's not the conjugate base of formic acid. The conjugate base is over here. It's the deprotonated form of the formic acid. So here we have a conjugate acid-base pair. And here we have a conjugate acid-base pair. I didn't write conjugate acid on the hydronium yet, but here we go. All right, so that should be the solution for all of those. Now, there's a couple other really interesting things that we can discuss based on what we see in this slide. One of them is that I don't know if you noticed or not, but I showed this one was just a one-way arrow going straight forward, whereas these two, I put them as systems in equilibrium. So what's the difference and how do you know? Well, there will be a subsequent video on this, but the reason that the first one is a straightforward arrow is because this one is a strong acid, okay? Something called a strong acid. Whereas when it's in equilibrium, it's the more common example of a weak acid or base, okay? So really what it comes down to is because ammonia is a weak base, it gets the equilibrium sign, and because formic acid is a weak acid, it gets the equilibrium sign. But the first one is a strong acid, chloric acid, it gets the one-way arrow. More about that later. The other thing you might notice here is that although we're talking about Bronsted-Lowry acid-base systems, it does still satisfy the requirement of the Arrhenius acid-base definition because, and let me just change my color, because you can see this acid here still does produce H+ in solution, but it produces it in the form of H3O+. And H3O+ hydronium ion is synonymous. It means the same thing as H+. Okay. You can also see that the base here, NH3, ended up producing hydroxide ion, and we said that was the Arrhenius definition of a base if it produces hydroxide ion in solution. Same here with the acid, formic acid, it produces H3O+ or H+. So they work together, they agree with each other, like they should. Okay, just a note on this, that when you see the hydronium ion, okay, when you see H3O+, basically that is the same as saying a proton in acid-base speak, okay? And throughout a unit, a high school unit on acids and bases, you'll use these symbols and terms interchangeably, synonymously. You'll have H3O plus, and you'll say that means a proton. You'll have a proton, and you might say hydronium. So why is that? Why do we understand that they're the same thing? Well, remember, if you've got H plus in aqueous solution, right, that really means you have H plus surrounded by water molecules, right, if it's in solution. Well, what you hopefully know about a water molecule already is that it will form a hydrogen bond, which is what's represented by the dotted line, with any small positive thing that can get close to those lone pairs on the O. So basically, the H plus, the free proton, if you will, in solution, would always form this strong hydrogen bond association with the water molecule, and we might as well just call the thing H3O plus. That's a little bit more realistic as to what it actually is. So we use them interchangeably. All right, the last acid-base theory, and it is a really good one, but it's one that applies to more specific situations in chemistry when it comes to complex ions, and in biology a lot when it comes to associations of metals and complex ions that are a part of protein structures in the body. But so we're not going to focus, I'm not going to give you much on this. If you're taking AP Chem or IB Chem, then go find better videos on Lewis acids and bases that let you go deep. But basically, it says that an acid is an electron pair. Acids are electron pair acceptors, and bases are electron pair donors. The biggest functionality that always sticks in my mind about this is it helps explain why some random loose metal ions like iron 3 plus or iron 2 plus are actually acids, okay? Because if you get something that has free electrons around, that has lone pair electrons like the nitrogen on NH3, those metal ions will be able to accept those electrons and form a strong association, and that in itself will be an acid-base reaction. So you don't have to worry much about it. Just realize it exists. I hope this video was helpful as an introduction to acids and bases and looking at frameworks through which we can study them, and you should continue to study them, and we will continue to study them in subsequent videos.